it gives me great pleasure to introduce the first speaker, Richard Davis from Jodrell Bank, Planck results and Jodrell Bank's contribution. Richard.
Well, it's particularly nice to be here today, and especially with David introducing me, because David was the Director of Science at ESA at the time when we built this machine at Jodrell Bank. So the first comment is just to note that Jodrell Bank is part of the University of Manchester. I'm always being told off because I say Jodrell Bank and don't mention the university. So this talk is going to be a little bit along the lines of the guy who talked to us about the supernova results. I'm going to tell you the way it was, the sort of details of the practical side of Jodrell Bank's contribution, and then talk a little bit about the results. And if there's time, I'll say something about BISEC 2 right at the end. So this is all the groups that have been part of it. Manchester is there. It's this blurred thing just here. ESA's well represented. It's nice and big. I'll move on quickly. So these are all the people at Jodrell Bank who have been involved. Alfie Wilkinson here was our project manager. She knew nothing about space, and so to start off with, we had Chris Castelli from Mike Cruise's group in Birmingham, who came and taught us how to go into space, and eventually Althea had her wings after about, I think it was 6 months, and she flew then on her own, but still with conversations with Chris Castelli. These are the people in Manchester who are involved. Bruno Maffe there and Gianpaolo, they're involved with the HFI, the high-frequency instrument. I was involved with the low-frequency instrument. So we're one of the few places where both cameras on the Planck spacecraft are actually in the same institution. So this is the standard picture of the Big Bang. Just to show where we're looking at. We look back to this epoch, which is about 400,000 years after the Big Bang, the time of recombination. So this is what the objective of Planck was, and I think we've very largely succeeded with that. It was to measure the whole sky with an uncertainty on the temperature limited by what's referred to as natural causes. In other words, rather than fluctuations, rather than intrinsic or systematic detector noise. Notice it does say just temperature, so Planck is not the final word that can be said about polarization. There is room for another satellite, which we're currently, or a group of us are working on. So this sets the history with the discovery of Penzias and Wilson at the top, and the Kobe satellite, then WMAP, and then finally Planck. So it's third generation CMB space experiment. This is where Planck, it's sort of very close to that place. It's at L2. It's been put in a slightly different orbit now. So that's 1.5 million kilometers away from the Earth. It was interesting holding the bits of Planck in one's hand and realizing that these bits were going to go 4 times further away than Neil Armstrong went when he travelled to the moon. These are all the countries involved. It does indicate the USA and Canada off to the left, and there's an arrow to Australia, data link down to the south. And you can see from the different colouring that Manchester is one of the few that has both LFI and HFI involved. So it's a truly multinational project. So this is the transistor receiver, the LFI, which is what we built at Jodrell Bank. And just to sort of try to explain, one of the problems is these transistor amplifiers have a thing called a 1/f noise. This is red noise. It gets worse and worse as you look at lower and lower frequencies, 1/f. So we have to do something about that. So here's the horn, which splits into 2 polarizations. And then there's a reference load here, which is actually, we look at the can of HFI, which is at 4 Kelvin. Then there's this hybrid, which takes A plus B and A minus B. So through these amplifiers go the sum and the difference of the sky and the 4K load. And then there's two phase switches, and then another hybrid, which if you send it through another one, puts you back where you started. You might think, well, why have we bothered to do all that? Well, what we do is take the difference between these two signals in the data acquisition electronics. And because this is a fixed temperature, we regulate that temperature very accurately. It means since both signals go through both amplifiers as A plus B and A minus B, it means that the fluctuations, most of the fluctuations that we see are actually due to these amplifiers. But because this signal we know is constant, by taking the difference between these signals, it removes all this 1 over F noise from these individual amplifiers. And all we get left with is the thermal noise of the amplifiers and indeed the fluctuations in the microwave background. So I've gone through that quite quickly. I need to move on. That's basically how the radiometers work anyway. So this is one of our space qualified amplifiers. You notice you can't see any wires. There is actually, so this was an early stage, so this was our own homemade phase switch. It was replaced by a mimic phase switch later on, but all the wires are on the back. The front surface is all the RF. These are the bias signals coming down here into the transistors. The 4 transistors are there, 1, 2, 3, and 4. So that's the input there, and there's the output directly into the waveguide. This is the device that we use, the Cryostat, which is calibrated against the WMAP Cryostat. We involved Marian Pospieszalski from NREO, and we flew amplifiers to and fro across the Atlantic until we managed to get the same sorts of results for the noise temperatures as was measured by the WMAP team in NREO. And I think really, without Marian's help, we would have been in difficulty, particularly with the 44 gigahertz. So this is what we call the Frontend Module here. So I'll show you a blow-up of this. This consists of 4 amplifiers, 2 double hybrids. It's a complete unit that does both polarizations. And this is mounted on the back of a system, which is a cryostat. These are loads which we can temperature control, and there are 2 4K loads there. I'll show you a blow-up of that. So this is what I've referred to as the Rubiks Cube. It was designed by Dr. Frank Winder, who was our RF engineer. And you see these are the 4 amplifiers. This is one amplifier, this part in red, and there are 4 of them. There's another one here, and then there are 2 others upside down. There's the input hybrid there, and an output hybrid here, and it all fits together. I thought we'd have many iterations, but in fact, he got it right straight away. There was just very minor changes to the flight models from that first design. And incidentally, we launched the whole thing. Now, what am I doing wrong? Here we go. So, and yeah, it all worked basically. I often felt that we probably get 10% of it working. That seemed to be the success rate of this sort of electronics. And we really needed all of it to work to get the polarization to work. And indeed, it all went up. There were 5 front-end modules altogether, 3 at 44 gigahertz and 2 at 30 gigahertz. And they all functioned and continued working to specification right till the bitter end after 4 years when we switched them off. So this is the noise temperature. This dotted line here was the sort of theoretical noise temperature. You can see the individual transistors as a bit of a scatter between the different performances, but some of them are absolutely incredible. This is 30 gigahertz. And you can see noise temperatures here of 5 Kelvin. These were the lowest noise amplifiers ever made at these frequencies. And this is the gain of the various amplifiers. So this is the 44 gigahertz flight hardware. This is the FEM actually assembled, all gold plated of course. So you can see the tops of the amplifiers here, and there are two more underneath. There are some wires here that go in that carry the bias signals, and there are various little slots with the waveguide slots. That's on exit, and there's one there on entry, and then there's two others on the far end, which you can't see. This is mounted on the vibrator table at RAL, and so here's the table, and this is Alfie Wilkinson, the project manager, and this was the guy who operates, I've forgotten his name, it operates this thing at RAL. This vibrating table is big enough to put a small tractor on, and this is our poor little FEM attached to it with heart monitors all over it. They were accelerometers, of course. So we'd have to shake this thing. That's absolutely vital before you're allowed to fly anything on an ESA satellite to make sure, essentially make sure nothing falls off, really. But also, you like to know that it continues to work. So this is our little group of people at Jodrell. That's Eddie Blackhurst in the middle, and Frank Winder to the right-hand side is the engineer. This is the LFI gradually being assembled. So the hole in the middle is where the HFI goes. So these are all the transistor amplifier, all the transistor radiometers, I should say, 30, 44, and these smaller ones in here, 70. The 70 gigahertz ones were built in Helsinki. So the next slide, when I saw this, I was absolutely horrified, because that is the LFI, and that's what we launched. So there's all cables hanging everywhere, and there was a cryostat lid that went on the whole of this thing. This is the back end unit. Here is the sharp end, as it were. The horns are in there, looking downwards, so that there would be a pool of liquid helium under here. And these are the waveguides that carry the signals from the front end to the back end units. So this lot all had to be tested, and then it was put on a lorry and taken from Milano down to CSL in Liège in Brussels, and then onto ESA in Noordwijk, where it was rotated and various others, and eventually put on an Antonov plane, a Russian Antonov plane, and flown to Kourou and popped on top of the Arion rocket and launched. And he did so, and everything worked. So this slide really, I've said it already, these are the lowest noise amplifiers ever made at these frequencies. So this is the Planck satellite, but without any of the front-end units fitted. This is just gradually assembling the front end. So this is the HFI now in the middle of the LFI. There's the HFI. This is with Bruno Maffe. You can just about recognize him. And just to comment, although I had nothing to do with the HFI, that's the high-frequency instrument that works from 100 to 857 gigahertz. The blue is the goal. The orange was the goal. This is a logarithmic scale in performance. And the triangles is what was actually achieved. So they actually did far better than the requirements and actually achieved their goal. So the HFI was a big, well, both cameras were a big success. So this is Planck all assembled, all done. And this is I think, David, you showed some slide like this in Manchester, which shows the WMAP sort of performance, and you see it dies a death at the third peak of the power spectrum. This is L here, and you see it's only designed to work to the third peak, whereas Planck goes all the way out here. That is a simulation of Planck. I want you to remember that sort of detail, because you'll see what we actually measured later on. So this is where Planck was tested with the giant cryostat. It's an enormous cryostat, 6 meters in diameter here and 9 meters long. It's as big as my house. Here is Planck laid on its side, and here's a 4 Kelvin shield. You have to be very, very careful to make sure there's nobody left inside when you close the door, because after you close the door, you suck all the air out and you cool the whole of the contents down to 4 Kelvin. It's not very good for human beings. And here is the arrangement of the 2 satellites in the nose cone of the Arion. So we required the nose cone to come off, we required the Herschel to be ejected, and we required this cover called the cylinder to come off Planck, and then we needed Planck to come out. So a whole mass of stuff. I really must take my hat off to the ESA guys, because they put this thing, these two satellites, into exactly the right orbit with the minimum amount of fuel, and the whole launch procedure went very, very well indeed. This shows some of the stuff we've been working on. ADCs, A to C converters only are calibrated, are only provided with an accuracy of 1 in 10 to the 3, given the bits as you change from bit to bit. And it turns out Planck actually needs 1 part in 10 to the 5. So we've had to derive ways of measuring this. So this was the sort of first sort of performance with the different methods of measuring the gain. You could see they all disagreed with each other. And after we've fixed this up and calibrated the whole thing in space, that works very well. Having a bit of trouble getting this to. I'll move over that one and that one. So this is the Sunyaev-Zeldovich. So talking about the results, some of the results now, the SZ measurements give you some determination of omega m, that's the mass in the universe, and sigma 8, that's the clustering on 8 megaparsec scale size. And you can also determine that directly from the CMB. So there are two methods, and you can see the SZ numbers disagree with the CMB numbers. And this is a well-known phenomenon. It's not just Planck that sees this. You can see these errors are very small with Planck. It's quite clear that there is a problem. And so there's two possible ways to put this right. It means we might need to change the YM relationship, which is that which calibrates the amount of mass from X-ray temperature. But you have to change it by an enormous factor. You don't just change it by 10%, you've got to change it by a factor of 2. The other proposal, which Richard Batty out of Jodrell Bank is very keen on, is to say this means that there's got to be some limit on the mass of the neutrino. And in fact, he and Adam Moss have just published a paper in which they've even proposed the presence of a sterile neutrino at a half in EV, and this, with the other active neutrinos, much lighter, and this actually, that should be lowers. It doesn't lower, it lowers the tension, because there is a tension of the H0 value, which Planck measures. So these are the 9 frequency channels of Planck. I'll just show you them briefly. That's a very important. There's all 9, going up to 857 gigahertz. You see the higher frequency ones dominated by dust. The lower frequency ones are dominated by synchrotron. And somewhere in the middle is the Goldilocks spot where the CMB is the thing we can see the most. And that's when we remove all the foregrounds. That is our map of the cosmic microwave background from Planck. So this is the power spectrum that we actually measured, and it's fitted with our model, which is what produces all the cosmological parameters, and it really is a beautiful fit. So these are all the numbers. I'm not going to go through all these, but just to point out that the omega baryon has got up. So hooray, there's a bit more of us. There's a bit less of this dark energy, whatever dark energy is. We have absolutely no idea what it is. Of course, everybody's looking for the dark matter as well. So there's a whole series of results there, including the Hubble constant. And these are more of those figures. I'm not going to go all through all those. They're all in the parameters papers of Planck. All this material I'm showing you is actually published. These are the Planck clusters, the Sunyaev-Zeldovich clusters. This, I think, is probably one of the most exciting results. I think a very beautiful result that's come out of Planck. So imagine if you're in your bathroom and you've got this glass which is there to stop people being able to see you through your bathroom window, but you look out and you could just about work out when the milk float's going by. So that we get the same problem in our universe, that we don't see the universe as it really is, because all the light is bent on the way by the massive galaxies. And so what we try to do is look at these distortions, to look at the image of the milk float, if you like, out through the bathroom window, and we try to work out what the distortions are caused by the bathroom window. So these, just to show that we can do it, so these are just two frequencies of Planck, 143 and 217 gigahertz. And if you look, you could see this is the actual deconvolved lensing potential. So this is about 1 sigma. Even though the fluctuations are measured to about 10 sigma, trying to deconvolve and get the lensing signal out is extremely difficult. But you could see there are things here which repeat. It's not perfect because we've only got about each of these images is only about 1.5 sigma. But we can see the lensing signal. And this is if you take the whole sky, and these squares that are on here are the power spectrum of the lensing signal. And then the line that's put through it is what we would predict from our power spectrum of the fluctuations. So it fits absolutely perfectly. So I think that's one of the most exciting results that has come out of Planck. And then this is, if you take the power spectrum and we multiply it by L squared, so this is actually the first big peak here. So where L is very small, it weights down the first peak, and it weights up all this interesting stuff at high L values. And what we've done is plotted on here the run in the spectral index, and theoreticians say inflation says it should be 1, but then when you ask them about it, well, they say no, it shouldn't really be exactly 1, it should be a little bit less. And this shows, so on this graph we've got the blue curve, which is n is 1, and you can clearly see that at high L values it doesn't fit. It fits the pink curve, which is at the top, which is an NS of 0.96, and indeed that is what we measure for the run in the spectral index. This is the run in the spectral index of the density fluctuations in the early universe. So this is the Hubble constant. So again, this is where we got our tension. So Planck's actually consistent with WMAP, albeit with a lower error, and indeed there'll be a new Planck result out soon from the new papers, which will have an even smaller error. But there is some tension here with these Cepheid and Carnegie measurements. You see these error bars don't quite overlap, although I think all these error bars are 1 sigma, so it's not really that bad. Anyway, if I just move on, just finally talk about these other numbers. So at the top, you've got the 0.9585 plus and minus 0.0070. You see the enormous precision that comes out of Planck. Here's the Hubble constant. We're now measuring 67 plus or minus 1. So I mean, a while ago we were looking at plus or minus 50%. I remember the arguments between Hubble constant of 50 or Hubble constant of 100. We've now got much more precision. Here's our omega m, which is much higher, and this is the sigma 8 value. So as I said here, there's the Hubble constant has about a 2.5 sigma level mild tension with the SNLS type 1a supernova measurements. This is the last slide of what I was going to talk about, which talks about, again, we've got this NS value and an effective, if we don't have the sterile neutrino, of a 3.36. So it's strongly encouraging along the line of 3 types of neutrino. And there are comments down here about the variation of the fine structure constant. I've just tried to summarize from the sort of 27 papers that were published the main results that have come out. And how much longer have I got, David? No minutes. Right, so then I'll just finish then by showing this final slide, which I've just put on here. So I thought I ought to say something about BICEP 2, this new result, which claims to have detected B modes, which is a smoking gun of inflation. So that we, as you can imagine, Planck is beavering away. We have sharpened our swords and we're working away like mad to come up with some results. Planck measures polarization. It is in our scientific objectives to detect and set limits on these B modes. Planck sensitivity, in principle, we ought to be able to measure the sort of signals that BICEP2 claims. Though in practice, this depends on controlling the systematic errors, and that's what we're working on, and indeed the foregrounds. And we plan, so I can't really say any more. We plan to release all our data, including the polarization maps, at the end of October. And just one very final comment is BICEP2 is based on one frequency, essentially. There's a little bit, it's 150 gigahertz, and they have a little bit of observation at 100, although not very much. And just as a final comment, Planck has got 9 frequency channels. And I think I'll probably better be quiet there and not say any more. Otherwise, I'll be shot. Thank you very much.
It's a very gentlemanly presentation. Questions?
Am I right in thinking also that BICEP2 only actually looks at a very small area of sky, which is particularly clear, whereas Planck will give us a complete sky survey?
That's right. I think it's about 50 degrees by 10 degrees. It's still a fair chunk of the sky, but it isn't the whole.
That's the isotropic.
Yes. Yeah. Whereas Planck is imaging the whole sky.
Okay. Anyone else? Yes.
Well, congratulations on a fantastic achievement. Just a detailed question. I hadn't heard before about the sterile neutrino, and I wondered what particle physicists' view of that was with reference to the standard model and so on.
Well, there are some measurements. There are some particle physics. I'm sorry, it's not my field, but there are some particle physics measurements that do claim to have detected the sterile neutrino. I think they work by, they know how many neutrinos they produce, and then they can detect the 3 different types of active neutrino, and by adding the sums up, they know they're missing something. So, because the sterile neutrino doesn't do anything, you can't react it with something. So there are some experiments that give you an indication that there is a sterile neutrino, but I don't really know what status that they are. I think the whole business is a bit wibbly-wobbly at the moment. Yeah.
Okay. Anyone else? Last question. Down at the front here. Yeah, use the microphone for the recording.
Just on information, the peak of the microwave backgrounds is what, just under 200 megahertz. So the 2 channels that you're using are more or less equidistant from the peak energy.
So the peak is at 200 gigahertz.
Sorry.
Yes, it's okay. So yeah, what we refer to as the CMB frequencies are the 70 gigahertz, 100, 143, 217, and 353. We start seeing a lot of dust at 353.
Yes,
if
sure.
you go much lower than 70, you start seeing a lot of synchrotron.
Yes. What I was interested in is that you showed images which you referred to as looking the milk float through the bathroom.
Yeah.
Now, I take it that those were the nearest below and the nearest above the actual peak frequency. Is that right?
They're actually both below. No, I think
No, they're not.
it was one was 143 and the other was 217. Yes, 217 is actually at the peak. 143 is just below.
Yes. Super.
Okay, I'm going to draw a line under that. Thank you very much, Richard.